The universe is a vast and mysterious place, an endless expanse that stretches beyond our wildest imaginations. It's filled with swirling galaxies, exploding stars, and cosmic wonders that boggle the mind. These phenomena, both familiar and strange, are only beginning to be understood by our ever-curious minds. Yet, amidst this cosmic chaos, there seems to be an underlying order, a hidden symmetry that governs the dance of the cosmos. A fundamental principle governs the workings of everything from the smallest atom to the largest supercluster of galaxies, the law of conservation of energy. This principle is the cornerstone of our understanding of the universe. This law states that energy cannot be created or destroyed, only transformed from one form to another. It's a concept that ties together the micro and the macro, the quantum and the cosmic. It's a bedrock principle of physics, a cosmic accounting system ensuring that the universe's energy budget always balances. This balance is what keeps the universe in a state of equilibrium, a delicate harmony that allows for the existence of everything we know. But what happens when the universe itself seems to bend this fundamental rule? What if the very fabric of space and time challenges this principle? As we explore the farthest reaches of space and time, we encounter phenomena that challenge our understanding of energy conservation. These anomalies push the boundaries of our knowledge and force us to rethink our theories. The expansion of the universe, a phenomenon that stretches the very fabric of space, the stretching of light waves known as redshift, which alters our perception of distant galaxies, and the very nature of time itself, which seems to flow differently in different parts of the universe, raise profound questions about the limits of our current knowledge. These mysteries beckon us to delve deeper. Join me as we journey into the heart of these cosmic puzzles to see if the universe truly breaks its own rules, or if these apparent violations hint at deeper, even more awe-inspiring laws waiting to be discovered. Together, we will explore the frontiers of space and time, seeking answers to the questions that have puzzled humanity for centuries. To grasp the potential implications of a universe that seemingly defies energy conservation, let's first understand how this law operates in our everyday lives. Energy is all around us, in every action we take and every process we observe. It is the driving force behind the universe's grand dance. Imagine a simple act, throwing a baseball. This everyday action is a perfect example of energy transformation. As you draw back your arm, you store potential energy in your muscles. This potential energy is the energy of position, waiting to be released. This energy is converted into kinetic energy, the energy of motion, as you release the ball. The muscles contract, and the stored energy is transferred to the ball. The ball soars through the air, its kinetic energy gradually decreasing due to air resistance and gravity. These forces act upon the ball, slowing it down and converting some of its kinetic energy into other forms. Finally, the ball hits the ground, transferring its remaining kinetic energy into sound and heat. The impact creates vibrations in the air, which we hear as sound, and friction with the ground generates heat. Throughout this entire process, the total amount of energy remains constant, simply changing forms. This is the essence of the law of conservation of energy. This principle applies to countless scenarios in our daily lives, from driving a car to powering our homes. Every action we take involves energy transformation. Gasoline, for example, stores chemical energy, which is converted into kinetic energy to propel the car forward. The engine burns the fuel, releasing the stored energy and transforming it into motion. Similarly, electricity, often generated from burning fossil fuels or harnessing wind or solar power, provides the energy to illuminate our homes and power our devices. Each method of generating electricity involves converting one form of energy into another. In each instance, energy is neither created nor destroyed, merely transformed from one form to another. This transformation is a fundamental aspect of how our universe operates. This constant exchange underscores the fundamental nature of energy conservation in our observable universe. From the smallest atom to the largest galaxy, energy is in a perpetual state of transformation, driving the processes that shape our world and beyond. The law of conservation of energy is not just a neat scientific concept, it's a cornerstone of our understanding of the physical world. It underpins countless scientific theories and technological advancements, from predicting the motion of celestial bodies to designing efficient engines and power grids. Energy conservation is a fundamental principle guiding our scientific endeavors. Moreover, it provides a framework for understanding the interconnectedness of different physical processes. For instance, knowing that energy is conserved allows us to trace the flow of energy from the sun to the earth, driving weather patterns, plant growth, and ultimately, sustaining life itself. This principle also helps us comprehend the delicate balance within ecosystems, where energy flows from producers to consumers and decomposers, maintaining the web of life. The conservation of energy is not merely an abstract concept, but a fundamental truth governing the very fabric of our existence. To fully grasp the potential challenge posed by the expanding universe to energy conservation, we need to introduce the concept of an isolated system. An isolated system in physics is a theoretical construct, a region of space completely cut off from any external influence or exchange of energy or matter. Think of it as a perfectly sealed box, impervious to any outside forces. Within this box, the law of conservation of energy reigns supreme. No matter what happens inside, no energy can enter or leave, ensuring the total energy remains constant. However, the universe as we observe it is not an isolated system. It's expanding, a fact confirmed by astronomical observations of distant galaxies receding from us at an accelerating rate. This expansion introduces a wrinkle in our neat picture of energy conservation, as it implies that the universe's total energy might not be as constant as we once believed. The expansion of the universe is not just an abstract concept, it has observable consequences, most notably the phenomenon of redshift. This phenomenon is a direct result of the universe's continuous growth, stretching the very fabric of space itself. Imagine the universe as a giant expanding balloon with galaxies scattered across its surface. As the balloon inflates, the distance between these galaxies increases, illustrating how space itself is expanding. As the balloon inflates, the distance between these galaxies increases. This analogy helps us visualize the concept of an expanding universe where galaxies are not moving through space, but rather space itself is growing. Now, imagine light traveling at a constant speed, journeying from a distant galaxy towards us. This light, emitted billions of years ago, carries with it the history of the cosmos. As this light traverses the expanding space, its wavelength, the distance between successive crests of the light wave, gets stretched out. This stretching effect is a direct consequence of the universe's expansion. This stretching shifts the light towards the red end of the electromagnetic spectrum, hence the term redshift. The greater the distance the light travels, the more pronounced this redshift becomes. Redshift is a crucial piece of evidence supporting the Big Bang theory and the expanding universe. It provides a window into the early moments of the cosmos, allowing scientists to trace back the universe's history. It also presents a fascinating puzzle when considering energy conservation. The stretching of light waves raises intriguing questions about the nature of energy in an ever-expanding universe. Light, after all, carries energy. This energy is a fundamental aspect of the light's properties and its interaction with the universe. As its wavelength stretches, its energy decreases. This phenomenon, known as cosmological redshift, implies that the light loses energy as the universe expands. So where does this lost energy go? This question challenges our understanding of energy conservation on a cosmic scale. This question lies at the heart of the debate surrounding energy conservation in an expanding universe. It invites us to rethink the principles of physics and the nature of the cosmos itself, pushing the boundaries of our knowledge and understanding. The concept of energy conservation is deeply intertwined with another fundamental principle in physics: time translation symmetry. This principle essentially states that the laws of physics are constant over time, unchanging and steadfast. In other words, an experiment conducted today should yield the same results if repeated tomorrow or 1,000 years from now, assuming all other variables remain the same. This might seem intuitive, but it has profound implications for our understanding of the universe and its workings. Time translation symmetry implies that the total energy of a system remains constant over time because the laws governing energy transformations remain consistent. This connection between energy conservation and time translation symmetry deepens the mystery surrounding the ever-expanding universe. If the universe's expansion affects the energy of light, does it also imply a subtle shift in the laws of physics over time? This question remains a topic of great intrigue. The expanding universe throws a fascinating curveball into the concept of time translation symmetry. As the universe expands, its overall energy density, the amount of energy distributed throughout space, decreases. This decrease occurs because the total amount of energy might remain relatively constant, but it's being spread out over an ever-increasing volume of space. This dilution of energy density creates a scenario where the universe of today is fundamentally different from the universe of billions of years ago. The early universe, shortly after the Big Bang, was incredibly dense and hot, a seething cauldron of energy. As the universe expanded and cooled, energy transformed, leading to the formation of stars, galaxies, and eventually, planets like our own. This evolution suggests that the conditions under which physical processes occur have changed over cosmic timescales, potentially challenging the absolute nature of time translation symmetry.